Okay, so this is lecture 8, and we are going to begin by talking about inverse functions. So what I said before is we have an equation that looks something like this, where there is a variable in the exponent, and how do we solve for that variable, right? So the first thing I can do is I can divide by 1,000, right? So if I divide both sides by 1,000, I get 2 equals e to the 0.045t. But how do I solve for t? So I have to have some inverse of an exponential function. All right, so first let's talk about inverses, and then we'll talk about the inverse of that exponential function. All right, so let's take a look at these two functions. I have f of x equals x squared plus 1 for x greater than or equal to 0. All right, so not the entire thing. So let me just graph what x squared plus 1 looks like. All right, so that's this parabola. But if x is greater than or equal to 0, then it would only be this part of the parabola. It would not include that part. And then I have this function g of x equals the square root of x minus 1. So the first thing I'm going to do is I'm going to compose these functions. All right, they asked us to compose f composed with g and g composed with f. So this is f of g of x, which means I'm going to take the function g of x and plug it into f. So I have square root of x minus 1 squared plus 1. If I square a square root, I'm just going to get what's underneath the square root. So I get an x minus 1 plus 1, and I'm left with an x. Okay, so my output was x. Now let's go ahead and compose g composed with f. So this time I'm going to take the function f and plug it into g. All right, so my function f is x squared plus 1. So I have the square root of x squared plus 1 minus 1. So plus 1 minus 1 gives me 0. So I end up with a x squared. And if I take the square root of x squared, I get x. All right, now remember I have x is greater than or equal to 0, so that I know that I can take the square root of that. So I end up with x. So when I compose both of these, I got x each time. And when that happens, that means they're inverses of each other. So if I compose f composed with g of x, and that output is x for all x in the domain of g, so all the values of x that are in the domain of g. We talked about when we were composing functions, the first thing we need to look at is the inner function. We restrict it to the inner function's domain, and then we compose it, right? And if I compose g with f, and I get x, for again, all x in the domain of the inner function, this time the inner function is f. If that happens, then they're inverses of each other, right? Because what we've been talking about is I want to be able to solve a equation, and I want to be able to solve for x. So if I compose them and they're inverses of each other, if I do the correct algebra or the inverse algebra of each step, then I should output x. And that's what I want to be able to do. All right. Now, one thing I want to note here, for the above functions, which means these functions that we had here, so let me rewrite them down. F of x equals x squared plus 1, and g of x equals the square root of x minus 1. Let's find f of 3. So if I plug in 3, into my function f, I get 10. So that point on the graph would be 310, right? Now, if I plug in 10 to my function g, the inverse of f, then I get 10 minus 1, square root of 10 minus 1, which is the square root of 9, which is 3. So if they're inverses of each other, if I have 310 in a function, then the inverse will always have 10, 3. All right. If I have the point 0.12, then the inverse is going to have the 0.21. All right. Let me also note that we write it as f to the negative 1. That's the notation for the inverse function. That does not mean, let me just write this over here. That does not mean 1 over f of x, right? We think of like exponentials, and the exponent, if it's negative, you can put it in the denominator. This is specifically a notation for inverse function. That does not mean 1 over f of x, all right? So make sure we know that. All right, so what we were saying, if xy is a point on the graph of f, then yx is a point on the graph of f inverse. So the domain of f is the range of f inverse. And the range of f is the domain of f inverse. So let's rewrite that. So the domain of f inverse is the range of f. And the range of f inverse is the domain of f. Right? Because when we talked about it, the values for the domain are all the x values, right? But if the inverse function makes those the y values, the range is all our y values. So the domain of the f inverse is going to be the range of f, and the range of f inverse is the domain of f. All right, so what do the graphs of them look like? The graph of the function f inverse is symmetric across the line y equals x. So we'll do an example so that we can see what that looks like. The graph of f inverse is a reflection of the graph y equals f of x across the line y equals x. So across the line where the slope is 1, the y-intercept is 0. All right, so across this line right here. All right, so first off, we talked about already that the graph of x squared plus 1, that's a parabola shifted up 1, and oh, I guess I didn't shift it over here. I should have. This should have been shifted up 1. All right, anyway. So I'm going to shift it up 1. Okay, tricky. Out of the way. Thank you. Shift it up 1. And again, x is greater than or equal to 0. All right, so it's only the x values that are greater than or equal to 0. So this is what my parabola looks like. Okay, now the square root of x minus 1. Now we know that the square root of x looks like this. And that minus 1 means I'm going to shift it to the right 1. Here, eat your treat. Please, thank you. So that is going to be this point, this graph right here. So notice that if you looked at them, so let me rewrite this. This is f of x, and this is g of, whoops. This is f of x. This is f inverse of x, or what we called g of x before, if you reflect it across this line, y equals x. I can't tell like which version you guys see, like if I'm backwards or not, but the line y equals x, if you reflect it, you get the same graph. All right, now let's talk about the domain and range of each of these. So this one's f of x, this one is f inverse of x. All right, so what is the domain of f? So the domain of f, remember, is the x values from left to right. All right, so the smallest x value is 0, and it goes on to infinity. All right, so the domain of f is 0 to infinity, and the range of f is the y values from bottom to top. So it starts here at 1 and goes off to infinity. All right, so now let's look at the domain of f inverse. Remember that the domain of f inverse is the same as the range of f. All right, so I need x values from left to right. And sure enough, that is 1 to infinity. And the range of f inverse is the same as the domain of f. So I need the y values from bottom to top, and that is 0 to infinity. Now, do all functions have inverses? That is not true. All right, so let's look at an example. So consider f of x equals x squared. All right, different from the one that we did because we're not restricting the domain, right? In this case, I'm not saying, okay, x is greater than or equal to 0. I'm saying x squared, so the entire function. All right, if I have f of 2, that equals 4, and f of negative 2, well, that equals 4. Okay, that's a function, that's fine, right? My x values didn't repeat. But now remember, if I have the inverse function, then my x and y values change, right? So f inverse would have 4, 2 and 4, negative 2. All right, so this would not be a function, right? Because my 4 does not have a unique y value. So this would not be a function. F of x does not, x squared, so f of x equal to x squared does not have an inverse. Now, if we restricted it to x is greater than or equal to 0, then that would be fine because that negative 2 would not be included, right? All right. So a function is 1 to 1. So how do I know if a function has an inverse? If a function is 1 to 1, it has an inverse. So we need to know what a 1 to 1 function is. A function is 1 to 1 if each value y equals f of x, and the range of f is assigned a unique x value. So let's think about this. If I am a function, then I have to pass the vertical line test, right? Now, if my inverse is a function, then it needs to pass the horizontal line test, right? Because remember, the x values and the y values switch. I need my inverse function to also be a function. So I need to pass the horizontal line test. So a function has an inverse if it is 1 to 1, and it must pass a horizontal line test. So that just means if I draw any horizontal line on the graph, it doesn't pass the graph more than once. If it passes the graph more than once, then it is not one-to-one. All right. All right, so how do we find the inverses? All right, so I'm going to show you writing the inverse, and then I'm going to show you the steps to it. I'm going to show you the steps and write them down. All right, so first of all, the first thing I'm going to do is remember that y is the same thing as f of x, and I'm going to switch x and y. So the first thing we're going to do is switch x and y. So switch x and y. All right, then what I want to do is I want to solve for y. All right, I'm going to cross multiply. Remember, x is the same thing as x over 1. So I have x times y plus 1 equals 2 times 1, which is just 2. Right, I'm solving for y. So I'm going to go ahead and distribute my x. So I have an xy plus x equals 2. Everything with a y, I'm going to put on one side. Everything without a y, I'm going to put on the other side. So xy equals 2 minus x. And now I'm going to divide by x. Y equals 2 minus x over x. All right, so this is solve for y. All right, and then write y equals f inverse of x. So my inverse is 2 minus x over x. All right, now, if you want to check to make sure they're inverses of each other, you compose them and make sure that you get x out. All right, so let's just do one of them. You can try g composed with f. Why don't we try f composed with g? Or f composed with f inverse. Sorry. So that means I'm going to take the inverse of f and plug it into f. So my inverse is 2 minus x over x, and I'm going to plug that into my function. So 2 over 2 minus x. Oh, I'm out of room. There we go. 2 minus x over x plus 1. All right. We don't want fractions within fractions, right? So what I'm going to do is I'm going to multiply both the numerator and the denominator by the common denominator in the denominator, which is x. So if I multiply 2 times x, I get 2x. If I multiply x times 2 minus x times x, the denominator and x are just going to cancel. So I'm going to get 2 minus x. And then if I multiply x times 1, I get x. All right, so in the denominator, I have a 2 minus x plus x. That simplifies to 2. And 2x over 2 gives me x. All right, so when I compose those, I got x out. Now, to go ahead and check f inverse composed with f to make sure you get x out as well. If it does, then we got the correct inverse, and we did. All right, now let's check. Let's try number 2. So number 2, we want to switch x and y. So x equals the square root of y minus 1. And I want to solve for y. So what I'm going to do is square both sides. So I have an x squared equals y minus 1. And then I'm going to add 1 to the other side. All right, so x squared plus 1 equals y. And then I'm going to switch y and f inverse. And in our case, it's g inverse because they named it g. So g inverse of x equals x squared plus 1. All right, now we need to check the domain of G inverse, right? Because again, G inverse looks like this. Right? And the graph of x square root of x minus 1 looks like this. All right, so we're going to have to restrict the domain of G inverse. So it is only the inverse if x is greater than or equal to 0. All right, now let me pause for a second. Okay, so now logarithmic functions. All right, so we have been talking about inverse functions because the whole time we have been thinking more about how do I solve for an exponential function? Well, the logarithmic function is the inverse of an exponential function. All right, so if I have a function that looks like f of x equals a to the x, where a is greater than 0, a is not equal to 1, and we know that those graphs look like this if a is greater than 1, and it looks like this if a is between 0 and 1. So first of all, does that pass the horizontal line test? And it does. So it must have an inverse. Well, that inverse is a logarithmic function, I'm sorry, which is log base b of x. So I use b instead of a. If y equals log base b of x, then I have b to the y equals x. All right, so this is how you rewrite them. All right, so if I have, remember, f of x is the same thing as y. So y equals log base b of x. Then if I write it in exponential form, that means b to the y equals x. All right, so let's do some examples. If I have log base 2 of 32, all right, so what is my base? My base is 2. My x value is 32. I'm going to rewrite it this way to see if I can find the y value. All right, so I have a base of 2 to the y equals 32. So 2 to the what power gives me 32? That would be 5. So log base 2 of 32 is equal to 5. All right, let's do the same thing with part 2, or with number 2. So my base is 3, my y is what I'm looking for, my x is 1 over 27. All right, so 3 to the y equals 1 over 27. All right, so 3 to what power gives me 1 over 27? You could think of it this way. Change to where they have the same bases. So 27 is 3 cubed. And 3 to the y equals 3 to the negative 3. So y equals negative 3. All right, now look at this question here at the bottom. What about log base 2 of 0? So my base is 2. I have my y value equals 0. Is there any value that I can raise 2 to that gives me 0? And there's not, because remember, there's a horizontal asymptote at y equals 0. There, 2 to the y is always bigger than 0 because it looks like this. All right, so this is not, 0 is not in the domain of log. All right, so what we're going to do here is we are just going to rewrite these in exponential form and logarithmic form. So this is in logarithmic form, and we're going to write it in exponential form. All right, so I have this form right here. I want to write it in this exponential form right here. So this is going to help us solve equations with logarithms in them. So you need to become familiar with this. All right, so this tells me 2 to the negative 3 equals 1/8. This one is n to the 11 equals 1/17, right? And to just reiterate, so this is where my base is 2, my y equals negative 3, and my x equals 1/8. All right, I got that from this form, and now I'm rewriting it in this form. This one, my base is n, my y is 11, and my x is 1/17. All right, and then I write it in exponential form. All right, you should pause and do the rest of these, and then I will go ahead and do them here. Okay, so part C, this is 169 to the 1/2 equals 13. Square root of 169 is 13. 5 to the k equals 50. And then this one doesn't have a base. So this is called, common log. If there is not a base, it is understood to be 10. Back a while before, calculators used to only compute in base 10, right? So on your calculator nowadays, you can change the base to whatever you want to, but if you use, do they even have log? Yes, they do have log. If you just put the log button on a basic calculator like this, it will always compute in base 10. Now your graphing calculators, things like that, you can change the base into whatever you want to. All right, so this means my base is 10 to the y equals x. All right, so this was logarithmic form into exponential form. Now let's take exponential form into logarithmic form. All right, so in this case, my base is 14, my y equals -2, and my x equals 1/196. So maybe let me rewrite this. Y equals log base b of x, if and only if b to the y equals x. All right, so it was in this form, and now I want to write it in logarithmic form. So I have -2 equals log base 14 of 1/196. All right, let's do the same thing for part B. So my base in this one is 6, my y is 3, and my x is 216. Let's write it in logarithmic form. So I have 3 equals log base 6 of 216. All right, so now you should pause and try these by yourself. Okay, so let's see. My base this time is x of 130. This time I have x equals log base y to the 72. And this one I have log, Triggy, what are you doing? Log base x of y equals -13. All right, so we know that a to the x looks like this, right? And we know that inverses are our reflection across the line y equals x. And I know that a to the x always has the point 0, 1. So the inverse function should have the point 1, 0. Right? And does this make sense? So y equals log base a to the x. So this means a to the y equals x. So if I plug in 1 for x, a to the what always gives me 1, and that's 0, right? So y equals 0. So that gives me the point 1, 0. All right. If 0, 1 is always in my exponential, the inverse function is going to have the point 1, 0. Right. And if my logarithmic, my exponential function has a horizontal asymptote, at y equals 0, then my logarithmic function should have a vertical asymptote at x equals 0. All right. So this graph is going to look like this. All right. Because it's a reflection across that line y equals x. So now let's talk about the domain and range and intercepts of my logarithmic function. Remember, this is my function y equals a to the x. This is my function y equals log base a of x. All right, so the domain. So I have a vertical asymptote at 0. So I can't equal 0, but I can be everything bigger. So the domain is going to be 0 to infinity. Now my range is going to be all real numbers, right? My lowest y value goes off to negative infinity. My highest y value goes off to positive infinity. So negative infinity to infinity. And we talked about this before. If 0, 1 is in my exponential function, then my logarithmic function will always have the intercept 1, 0. All right. And it's not going to have a y-intercept because there's an asymptote there. All right. Now, as x goes to 0 from the right, and remember what we mean from the right, it means from this side. As x goes to 0 from the right, where does that function go off to? It goes down off to negative infinity. All right, so we have 3 main properties of logarithms, but it's been written as 5. But these are your 3 main properties of logarithms. But let's think about this one here. If I rewrote this as an exponential, that means a to the y equals 1. We already said this, y has to equal 0. So it doesn't matter what base I have. If I have log of 1, the answer is 0. So log base 20 of 1 is 0. Log base 1,000 of 1 is 0, and so on. Now let's look at 2. Log base a of a, well, that means a to the y equals a. All right, well, that exponent, if I set my exponents equal to each other, that means 1. So if my base is the same as what's inside my logarithm, then I always get 1. So in other words, if I have a log base 23 of 23, then that equals 1. If I have a log base x of x, then that equals x, and so on. All right, so the 3 that are important that you will see a lot, if I have log base a of xy, so it doesn't matter what the base is, but I have 2 things being multiplied together, all right? This does not mean log base a of x times log base a of y. It has to be log base a of xy, 2 things being multiplied together. Then that is the same thing as log base a of x plus log base a of y. So you can write them as addition. Now, if you have log base a of x over y, then you can write them as a difference. log base a of x minus log base a of y. The one in the denominator is the one that you subtract. If I have log base a of x to the r, I can bring this exponent out in front. Right? If I have a log base a x to the r, then I can bring that r out in front. Log base a to the x. So remember back when we were saying, oh, we need logarithms to solve exponential equations. Well, remember we had something that looked like this: 2 equals e to the 0.045 t. Well, what we're going to be able to do is we're going to be able to take the log of both sides and be able to bring that exponent out in front so that we then can solve for t. All right, a couple inverse properties of logarithms. If I have log base a of a equals r to the r, well, remember I can bring that r out in front. And then we just said that log base a of a is always 1. So that equals r. So if I have log base a of a to the r, it just equals r. All right, if I have log base, or if I just have a log base a to the x, well, that equals x. All right, so we're going to use these properties to just simplify some of these expressions. All right, so first it says I have 5 to the log 5 of x squared minus 2x. Well, we just said if I have the same base and the same base of the logarithm, I just get what's inside that logarithm. So in this case, I just get x squared minus 2x plus 3 because I had 5 as my base and I had log to the base 5. So I just get what's inside that logarithm. All right, now this is a multiplication. And my multiplication, I can write as addition. I'm also going to write this square root of x as x to the 1/2. So I'm going to rewrite this as log base 5 of 125 plus log base 5 of x to the 1/2. All right. What is 125 if I have 5 as a base? Well, that's 5 cubed. So I'm going to rewrite this as log base 5 cubed. Now I can bring that exponent out in front. So I have a 1/2 log base 5 of x. And now we said that if I have log base a of a to the r, then it's just what's in that exponent. So this is going to be 3 plus 1/2 log base 5 of x. All right, now number 3, log base 4 of 4 plus x squared. Now I have a 4 plus x squared inside my logarithm. I actually can't do anything with this. All right, our property said if I was inside a logarithm with, let me pause. Sorry, we were barking at the trash can. All right, so inside the logarithm, I have a 4 plus x squared. Well, we don't have any properties when inside the logarithm there's an addition. We have when there's a multiplication and when we have a division, but not for addition. So there's nothing we can do here. So this cannot be rewritten. All right, we mentioned this before, but let's talk about two special kinds of logs. The common logarithm is log base 10 of x. So if you see a logarithm and there is not a base there, it's just understood that it is 10. All right, so if I had log of 0.001, well, this is log base 10, and 0.001 is 10 to the negative 3. So negative 3. Then the natural log is log base e. And we talked about e recently. that is just an irrational number, 2.718, and so on. We write it as ln of x. So ln of x, excuse me, is just log base e. All right, so if I have natural log of 1, well, we said with these properties over here, it doesn't matter what the base is, it's just 0. So natural log of 1 is 0. Now, natural log of e. Well, remember, this is the same thing as log base e of e. And if they're the same, then that equals 1. All right, now if I have e to the natural log of x, well, that's e to the log base e. I'm just going to get what's in that exponent, which is x. And then if I have natural log of e to the x, well, that's log base e of e to the x. You're going to get what's in the exponent, or you can think about it this way. I can bring my exponent out in front, and the natural log of e we just said was 1. So I also get x. So we need all of these properties to be able to solve equations with logarithms. All right. Question, if I have f of x equals e to the x plus 2 and g of x equals natural log of x minus 2, let's show that they're inverses of each other. All right, so we're going to do this in a couple ways. We're going to show it by composition, and we're going to show it by graphing. Okay, so first of all, let's compose. So f of g of x. So I'm going to plug g into f. So f of natural log of x minus 2. I get e to the natural log of x minus 2 plus 2. All right, so if I have e natural log of x minus 2, remember natural log is log base e. So I just get what's inside the logarithm. So I get an x minus 2, so plus 2, and that gives me an x. So that's good. Now we want to compose g compose with f, and we want them that needs to equal x as well. So g of f of x. So I'm going to take f, which is e to the x plus 2, and plug it into g. So I have natural log of e to the x plus 2 minus 2. 2 minus 2 gives me just 0, so I get natural log of e to the x. And we just said that natural log of e to the x is equal to x. All right, so I know they're inverses of each other because when I compose them both ways, I got x out. Now, let's go ahead and graph them. So let's start with e to the x plus 2. Now, e to the x has a horizontal asymptote at 0, but this one is shifted up 2. So my asymptote is going to be here. Normally, I have the point 1, 0, but I'm going to shift that up 2. So instead of 1, 0, I'm going to have 3, 0 because I shifted it up 2, right? So 1, 2, 3, 0. All right, so here's my graph. Just going to do a rough graph. All right, now I have natural log of x minus 2. Right, so we know what natural log looks like. It looks like the logarithmic equation that we just saw before. But we're going to shift it 2 to the right. Now, we also said there was a vertical asymptote at 0, but now we're going to shift that vertical asymptote by 2. So 1, 2. All right, now the logarithm always has a point of 0, 1, but now we're shifting it 3, right? So I had the point 0, 1, but I'm shifting it 2 to the right. So that's going to give me 0, 3. So I have this point here, and that graph is going to look like this. right? And here is my line y equals x, and you can see that they are a reflection over that line. All right, the next couple of examples are just simplifying. If I look at e to the 3 ln 2, now there's nothing I can do just in that form, but I do know if it's in front, I can write it as an exponent. That's one of our properties. E to the natural log of 2 cubed. Well, now I have the same basis, so I just get what's inside my logarithm. So that is just 8. All right, now this one, number 2, I'm going to write as several logarithms. All right, if they're being multiplied, I can write them as addition. If they are divided, I can write it as subtraction. So I have natural log of e to the 2x plus natural log of x plus 1 squared. And I'm going to write this one as x minus 2 to the 1/2. All right, I'm going to write that square root as a power. All right, now I'm going to bring all the exponents out in front. So I have a 2x natural log of e plus 2 natural log of x plus 1 minus 1/2 natural log of x minus 2. Now I know natural log of e is equal to 1. Pretty, you're just not being helpful today. So I am going to end with 2x plus 2 natural log of x plus 1 minus 1/2 natural log of x minus 2. All right, so we wrote it as several logarithms. So now, how do we solve equations with logarithms? All right, so there's 2 different types of logarithmic equations. So there's a version where I have a log on one side and a number on the other. So I don't have a logarithm on both sides. All right, so this is our first 2 examples. I don't have a logarithm on both sides. All right, so in this case, what we do is we write it in exponential form. If there's not logarithms on both sides, we write it in exponential form. All right, so let me just remind you. So if I have y equals log base b of x, that's the same thing as b to the y equals x. All right, now, natural log has a base of e. So e squared equals x plus 3. All I did was write it in exponential form. All right, and now I can solve for x. So e squared minus 3 equals x. All right. We're going to do the same thing to number 2. All right, so now I have a base 9 to the 3/2 equals x. All right, this tells me take the square root of 9 and cube it. So the square root of 9 is 3, and I cube it and I get 27. All right, now we have seen questions where if I have the same base, then I can write, so these aren't logarithmic equations, these are exponential equations. If they have the same base, then we set the exponents equal to each other. What we didn't do is, well, what if they aren't the same bases? All right, then what we do is we take logs of both sides so that I can bring the exponential out in front. So this is the type where I have a variable in the exponent. And you're going to take the natural log or the log, I always take natural log. And definitely if you have base E, you want to take the natural log. I'm going to take the natural log of both sides. All right, so I have 3e to the 5 minus x equals 2. So the first thing I'm going to do is I'm going to divide by 3. So I want the base on one side by itself, the one with the variable. 5 minus x equals 3 halves. All right, now I'm going to take the natural log of both sides. Natural log of e to the 5 minus x equals natural log of 3 halves. Right, I can bring that 5 minus x out in front, or remembering that natural log is the same thing as base e, so I get 5 minus x here equals natural log of 3 halves. So then x equals 5 minus natural log of 3 halves. Why do I have 3 halves? These should all be 2/3 because I did not divide correctly. I apologize. All right, so this is when there is a variable in the exponent. You have to take the natural log of both sides. All right, now we did these logarithmic equations when there was not a log on both sides. Now we have logs on both sides. What we're going to do is we're going to set the insides equal to each other. But they have to be just one log on each side. All right, it can't be like our first example, log plus log, all right, or log minus log. So you have to combine them using our properties of logarithms. So what we know about natural log of 2x plus 3 plus natural log of x minus 1 is, since they're added, I can write them as multiplication. Right, so I can write them as one logarithm. So you need to write as one logarithm on each side. Right, so on the left side, I'm going to write it as natural log of 2x plus 3 times x minus 1 equals natural log of 7. So now, since I have a logarithm on each side, one logarithm on each side, I can set the insides equal to each other. So 2x plus 3 times x minus 1 equals 7. All right. Now I need to FOIL out the left side and set it equal to 0. So let me just remind you of the zero product property. The zero product property just says if I have x times y equals 0, then x equals 0, y equals 0, right? So people sometimes forget and say, okay, well, if xy equals, in our case, 7, then set x equal to 7 and y equals 7. Well, that's not true because there's an infinite number of things that I can get together to multiply to get to 7. But if it equals 0, one of them has to be 0, right? So remember, I can't set 2x plus 3 equal to 7 or x minus 1 equal to 7. I have to FOIL it out and set the entire quadratic equal to 0. So that's what we need to do. So let's FOIL. First is 2x squared. Outer is minus 2x. Inner plus 3x. Last minus 3. And then bring the 7 over and add like terms. So 2x squared plus x minus 10. All right, and I'm going to use the AC method, which means I multiply A and C. So I need two numbers that multiply to give me negative 20 and add to give me a positive 1. So I believe that's 5 and negative 4. So let's see here. I have a 2x squared plus 5x minus 4x minus 10 equals 0. Right, and then we're going to factor by grouping. I'm going to group the first two, and I can factor out an x, and I'm left with an x plus 5. And the second two, I can factor out a -2, and I'm left with an x plus 5. Factor out my x plus 2x plus 5. There we go. There we go. Let's retry that. First one, I can factor out an x, and I'm left with 2x plus 5. The second one, I can factor out a -2, and I'm left with 2x plus 5. So I factor out a 2x plus 5, and I'm left with an x minus 2. So I get 2x plus 5 equals 0, and x minus 2 equals 0. So x equals -5/2, and x equals 2. Now, with logarithmic equations, you can do all the steps right, but your solutions may not always work, right? They could be an extraneous solutions. Because remember, everything inside a logarithm needs to be positive. If I were finding the domain of a logarithm, for example, the log of x squared minus 4. Remember, my normal logarithmic equation looks like this. Everything is greater than 0. So if I were finding the domain, I would say, okay, well, x squared minus 4 must be bigger than 0, all right? And we know how to solve inequalities like this. So if I plug in one of these solutions, and I end up taking the logarithm of something that's not in the domain, something that's negative, then that's an extraneous solution, and I have to exclude that solution. So we're going to check. So let's start with x equals -5/2. So I have natural log of 2x, 2 times -5/2 plus 3 plus natural log of -5/2 minus 1 equals natural log of 7. All right, I can see right here that I have a natural log of a negative number. I'm going to get a natural log of a negative number here as well. So -5/2 is not a solution. Now let's go ahead and check x equals 2. So I have natural log of 2 times 2 plus 3 plus natural log of 2 minus 1 equals natural log of 7. All right, well, natural log of 2 minus 1 is the same thing as natural log of 1, and we know natural log of 1 is 0. So now I have what did I do wrong? Oh, I missed a parentheses. There we go. So I have 2 times 2, which is 4, plus 3, which is 7. So natural log of 7 equals natural log of 7, and that's true. All right, so my solution is x equals 2. All right, now let's go ahead and find the inverse of a logarithmic equation. So remember, y and f of x are the same. And now I'm going to switch x and y. X equals 3 natural log of y minus 4. And now what I want to do is I want to solve for y. All right, so I'm going to add 4 to both sides. X plus 4 equals 3 natural log of y. And I'm going to divide by 3. So I have an x plus 4 over 3 equals natural log of y. Now, how do I solve for y? All right, so remember, I can now put it in exponential form. So e, because the base is e, to the x plus 4 over 3 equals y. So all I did was use our formula. It was in logarithmic form. I put it in exponential form. e to the x plus 4 over 3 equals y. And now I rewrite y as f inverse of x. All right, so I feel like we covered a lot of information. A lot of people struggle with solving equations with logarithms and exponentials. So if you look on your Unit 1 page, I went ahead and have an extra worksheet there if you want to practice some other ones. All right, have a good day, guys.